Hello, everybody. Hear me well? So today we have our last lecture, Q&A, last chance to ask any questions, last chance to, um, you know, prepare. Well, the exam is on Monday, so the today and the weekend is left. Uh, we have put up the poll for the retake exam, and I think we got the most votes for Friday, 27th of January. So I think that's when it's going to be. We are having at least double amount of people from last year who are coming to the exam, so that's very nice. So the course is increasing in popularity. Okay, so I received questions from you. Thank you for the questions, and we will go through them one by one. I hope we'll get to all of them. It's not so many, seven questions, but actually pretty difficult, pretty good questions. Um, okay, okay, so let's go with this. Okay, so the first question, is it possible to define um, a Hopfield network which would implement the logical gate AND? Now, it's a good question, and I don't know. So, actually, I didn't start searching online. I just tried to think about it myself. I don't know what happens if you search online, but I thought about it myself, and so here's what I came. I have kind of an answer. Okay, so what's the question? Let's be clear. Actually, this question is not very precise, but so we know that the in the perceptron or the McCulloch bit units or like a neural network of sorts, you can always create an AND gate. Okay, so how does it work? You put a threshold, let's say 2, and you put weights 1 and 1. And then if your inputs are anything but 1 and 1, okay, so the inputs here are in the binary set 0 and 1. Yeah, so we have 2 bits coming in. And if the bits are the same and they're both 1, then you have 1, then what the network will, in the first step, you'll have 1 times 1 plus 1 times 1, and that is at least 2. So you will output 1, and in every other case, you'll get 0, right? So then this network implements the AND gate, because if we make this kind of a table, we will see that we have this kind of output, and that's AND. Okay, everyone's following. If you don't follow, just ask a question, whatever. Okay, so the question was, can we do the same with the Hopfield network? The way I understand the question is that, can we make a Hopfield network which has many neurons, and we select 3 of them. So let's say this neuron and this neuron and this neuron. And we want that this network works so that when we initialize these 2 to be something, then this will eventually, in the stabilized network, it will reveal whether this was an AND or no. So basically, if both of these are 1, if we're initialized to 1, then this will be 1. And if these are both initialized to something else, then both 1, then this will be 0. And that's one way to interpret the question. So if that's how we interpret the question, then I don't know. But I think the answer is no, you cannot, because Hopfield network has the property that any stable state can be flipped around. So if this is a stable state, then also minus S is a stable state. So that is a property of Hopfield networks. And so if we have this kind of network, and now let's assume that we have these 3 neurons, like, I mean, ideally you would have a 3 neuron network. But so what happens now is that if it detects AND, then when these both, the idea would be that when these both are initialized to 1, then this will become 1. Okay, and every other case, this will become 0. So that means that if I have the same network, let's assume we have some weights, just so that the picture looks clearer. So that means that if this is 1, then this should become 0 eventually. Oh, I think, let's see. So I really thought about it for a while, but because you really need to think, because there are so many options how you would actually do it. Yeah. Okay. So suppose that we start with this. So then this should become black, or it should become 1, or green in my case. If this is a stable state, sorry. This should become 0 because this is not, so this is 1, this is -1, so it's not AND, so this should become 0. So if this is a stable state, then also the complement is the stable state. So then also this is a stable state because this is a complement. And that's wrong because now this also fails the AND property, but now this is 1. So this cannot be a stable state, right? Okay, so we have a problem. So the only thing that could happen is that somehow this one gets destroyed, and then this converges to this stable state, which is empty. Okay. But why would this get destroyed? If this gets destroyed, yeah, I don't know, man. There is a chance that if we there is a chance that we can design a network such that we initialize this answers node always to 0, and the other ones we initialize to our input, and then we let it Then we let it kind of stabilize. But how we prevent, for example, this converging to this? Anyone has any ideas? If you have any ideas, you can comment. I'll make one more attempt, like to think about this live right now. And if it fails, then we will move on. And if somebody has Googled this or asked ChatGPT or whatever, please tell me if you have an answer. Okay, so let's see. So my attempt would be to do something like this. I want that if both of them are 1, then this third one will become 1. And by the way, in Hopfield networks, the weights are always symmetric, which makes it more difficult. So at least I want the situation where I have some connections here. Let's say weights 1, 1, and then I have a threshold 2. So then if both of these light up, then this also lights up. But it's not enough, because if these both light up, what if my next node that I'm updating is this one? I don't want it to disappear. So it should not disappear. How do I make sure it does not disappear? Well, now it receives only input from this -1 node, so it would disappear if I don't do anything. I could do two things. I could increase its threshold. Okay, let's try that. I increase its threshold. So I put the threshold here to be 2. So it can never be destroyed. But if it can never be destroyed, then we have a problem in the other case. But okay, but suppose I strengthen it by saying that there is a connection here, and this connection is -1. No, -1 or 1. What do I want to put here? Maybe I want to put 1. Okay, let's do this. Okay, so let's try this. And this threshold here is 2. Okay, so now, for example, these upper nodes will not change if they are updated, because okay, they receive -1 from here, they receive 1 from here, from the other one, so it's 0, the threshold is 2, nothing will change, fine. But if I update this node, it will flip to 1, and that's stable state. So now this one will give me the right answer. Okay, very good. What if I start with this being active and the other one being not active? So, okay, so now if I remember in Hopfield network, we update these nodes in a random order. So we have to take that into account. So I suppose I start from this. Now, if I update this one, oh, now it receives -2 because it gets -1 from here and -1 from here. So it becomes 0, and that's good because we want to destroy. This is not we want it converge to 0 state. Okay, so this will go to 0. So that's good. Let's see if I can do it like this. So if that's 0, this is a stable state. Everything receives -2 from everyone, and so this is a stable state. Okay, what if I update this first? This receives -1 and 1, nothing will happen. And if this is updated, nothing will happen. So yeah, okay, great. So this will converge actually to the zero state. Oh, okay, so actually this works. Okay, this works. But it only works because I am assuming that in the initialization, this bottom node will always be initialized to 0. Okay, very nice. So let us we can now do this. Look. I can draw. I skip the weights now, and I will make this smaller, and I will draw all possible initializations, and then I'll say, okay, look, and then I have this, which is the full activation, and now we see that this will converge to this, and all these will converge to this, and this is stable, and this is stable. Okay, so it works. Okay, so the answer is yes. You can do it with this network, and you just initialize it. So you have an input x1, x2. You initialize your network like this. You put 0 here, and you put x1 here and x2 here, and then you wait until it stabilizes, and then if the answer, if the stable state is this, then the answer is no. And if the answer is this, then it's yes, and that's your AND gate. Okay? Good. Question 1 covered. Question 2. Hopfield networks have limitations such as low memory capacity. Can the networks be modified to be more useful in practice, or are better alternatives used? Okay, so good question. Indeed, Hopfield networks, they have a theoretical limit for the number of stable states that they can store. The one that I just showed had 2 stable states. But in practice, actually, they store less than the theoretical maximum, because usually the stable states you want are not they are not orthogonal to each other, so they can overlap too much, and so the Hopfield network kind of is has a poor capacity in that sense. But so I found out that there has been breakthroughs in this. So in this paper, Hopfield himself and some co-author Krotov improved the capacity. Again, I don't know, I didn't obviously have time to read this. I don't know how they do it, but they somehow improve the capacity of the network. This work has been followed up by later work. Here we can see some pictures. Okay, but indeed, I cannot really answer. Another answer to this question is Boltzmann machines. So Boltzmann machines are basically generalizations of Hopfield networks. Not sure which one came earlier. Um, looks like Hopfield was earlier. So anyway, both are based on physics. So Boltzmann, as you know, was a physicist, and Boltzmann, it's called Boltzmann machine because it's kind of a statistical. Both Hopfield networks and Boltzmann machines are based on statistical physics, But Hopfield network is not statistical, right? So it's just binary zeros and ones. The only random thing is that you update the weights randomly, but there's no probability distribution. The values are not random variables. They're just zeros and ones. But the whole idea comes from the Ising model. I don't know if Nicoletta spoke about this or not. But so the whole inspiration came from the physical model of spin distributions. So Ising model. Here's Ising model. Okay, so imagine you have a grid of magnets. Each magnet can be rotated minus or plus. So it can spin. It can be spin up or spin down. Let's see if we have a picture somewhere. Picture. Well, this is basically a picture. Okay, here we have a picture. Okay, so imagine we have this kind of a grid with magnets. Each magnet points up or points down. They really point towards you or away from you in this picture. And of course, the magnets spread their magnetic field around them. And so whenever some magnet is facing up, it will push the neighboring magnets also to look up. But if some magnet has is facing down, then it will try to bring the neighboring ones down. And then imagine you let them update, so you let them just basically go with this magnetic field which surrounds them. And you can ask, are they going to approach some kind of stable equilibrium where they're not going to flip anymore? So each magnet has 8 neighbors. So it can happen that one magnet has 4 neighbors are pointing up and 4 neighbors are pointing down, and then that magnet, supposedly would not flip either way because the total magnetic force from the neighbors is 0. So they will not converge to like all being up. They just converge to some stable state where the force applied to every magnet is either 0 or is aligned with its own spin anyway. Another interesting version is where you fix the magnets on the boundary, for example, by some force, external force. So the magnets on the boundary are forced to be in a certain position, and then you look at the internal distribution of the magnets. So in this way, you can implement like a very simple network. Now, the problem with that is that you cannot control the weights and you cannot control the connections. The connections are based on proximity. So when 2 magnets are close, they influence each other. When far, they don't influence each other. And they influence each other with a fixed weight, which is dependent on the distance. So the idea of Hopfield was pretty much just to take this, put it in a computer, where now suddenly we can manipulate the weights and the connections. And so now we can have more flexibility in the stable states. We can program it to have whatever stable states we want, etc. So this is the whole idea behind Hopfield networks. Now, the real Ising model is much more complicated because there's also temperature. So in physics, as we know, it's not only a magnetic field, it's also temperature. Temperature means that every magnet randomly flips up and down. And when the neighboring neighboring magnets change the distribution of where they point up or down, let's say 60% up, 40% down, then the distribution of that magnet also changes. And so they instead of pointing in one direction, they have like probability distributions of where they're pointing, and they point in random directions. If the temperature is very, very high, then it overrides the magnetic field, And then the whole Hopfield net, or this Ising network, is just random. And when you decrease the temperature, at some point there is like the whole thing fixes in some position, which is a stable state, which is called in physics, it's called phase transition. The whole, if you simulate this in a computer, it's called simulated annealing. Here's a keyword for you. Basically, simulate the physical process of this happening. If you heat up, if you take a metal piece, it can be magnetized. You know, if you take a magnet and you bring it close to a metal, then it will magnetize. If you heat up the metal sufficiently hot, I think it's like 770 degrees Celsius. It's not easy to do that. But if you heat it up very, very hot, then it will not magnetize anymore. So that's the reason. Okay, so Boltzmann machines are taking into account the temperature factor. So they are more efficient in some sense, more flexible, I guess, in many ways than Hopfield networks, because they have these probability distributions built in. But the mathematical idea is the same. So there is an energy function, it goes down, here's the temperature, whatever. And also, I think in Boltzmann machines, they typically have some kind of hidden state. So it's not just like Hopfield network would just have those visible states that the user is interacting with, like all these states are updating. While in Boltzmann machine, you additionally have some hidden states which are fixed into some configurations. I think, I'm not sure how it works exactly, but that is another approach to the same idea, and it kind of is maybe more efficient. I would imagine that it also has like a larger memory capacity than Hopfield networks. Okay, so that hopefully answers this question. Let's move on. Question 3, backpropagation. Okay, let's review backpropagation. How is backpropagation used to update the weights in a neural network? I would like a refresh on this topic. So fair enough. Okay, so whenever we want to apply backpropagation, it's because we want to basically find a local minimum. We view the network as outputting a error. Okay, so is this working? No, it's not working. Why is it not working? It's beyond. Is this working? It's not working. Okay. Why is this not working? Okay, so we have a network. Let's have a very simple network. And we put in something and we expect something out. X goes in and we want to have Y. Now, we want to have a particular y. So what we're going to do is that we put another layer here, which basically, okay, so sorry. Here we have output. Output, let's denote output by y hat. And then we have some value which we want. That's the label. Because it's supervised learning. So then what we do is that we put one more node, and this node just takes y hat minus y, and maybe takes, the absolute value and square or something. So that's the error. Okay, so now the network, instead of outputting what we want, it actually outputs the error from whatever we want it to output to what it actually outputs. So this is the network to which we applied the backpropagation. Let me remove this. All right. Okay, so it boils down to just minimizing the output. Well, so how do you minimize an output? So suppose you have a two-dimensional function, just for the sake of the argument. It's just not really working. Okay, I'm going to draw a straight line like this, and I have two-dimensional function, and let's say if I were to draw the level curves, it would look something like this. This is my function. So it has a minimum over here. And we have a landscape that it goes down there. Okay, so now let's say I randomly select a point. And now I want to know where should I move my point so that I get closer to the minimum. And I'm allowed to take derivatives. I'm allowed to take derivatives. If I take derivatives, I can see that the derivative at this point in the landscape is pointing this direction, let's say. It might not point directly to the minimum, but it points somewhere in that direction, hopefully. Well, at least you go down if you go along not exactly the gradient, the negative of the gradient, because the gradient always goes up. So we take minus the gradient, so then we go down. So then we just apply that vector, and so we move lower in the landscape. Okay, how does this translate to the neural network? The neural network has weights. It has weight, let's say in this case, is just 1, W1, and W2. That's all we have. Okay, so this whole network is a function denoted by big phi. It's a function of the input and the weights. Okay. Now the input is fixed. That's the data. And so we are manipulating the weights so that this whole function becomes as small as possible. So then the error is as small as possible. And when the error is as small as possible, we will chop off this part. And then the remaining part is network that outputs the correct answer. So this is a function in two variables. So this is exactly this. So it's two-dimensional function with two variables, W1 and W2. And then by taking the gradient, we can move towards this point. What is gradient? Gradient is a partial derivative of this with respect to one of the variables. That will tell us which way to move this coordinate. Is it up or should we move it down? In this picture, it would be up because we're going close here, this way. And the other coordinate is the same thing. Partial derivative with respect to W2. So then that will tell us which direction to move this coordinate. Is it left or right? In this case, it's left. Okay. So backpropagation will give us those partial derivatives. And backpropagation is kind of nice because when we backpropagate the derivatives, according to chain rule, we just multiply them, multiply them, multiply them. At each stage, you can, by multiplying whatever is backpropagated from the right to this point by this weight, you get exactly this. It's this consequence of the chain rule. Because this is basically a composite function. The further you go in the network, the more it's like composite, and composite functions, you take the derivative by multiplying by the derivative of the internal function, then multiplying that by the derivative of the internal function of that, and so on and so forth. So if we have like a large, okay, so that's the idea, okay? So for this case, it should be clear. We just take when we backpropagate the error, that means that we're taking the derivative of this whole function with respect to these two weights. And so I guess let me show what happens if I have like a very, let's say, large network. Something like this. Now, suppose I have a derivative over here. This is a derivative of this entire composite function. So I figured somehow it came, if this is the last node, the last node was this error, remember? So we just take the derivative of this with respect to this y hat, which is the input from the previous layer. And the derivative of this is just 2 times this. Basically, that's it. And so you send this back, and then here you have some node which it actually was the one that put out, like this is the error. Let's start from so this was the error, and you backpropagate. This is the error, and you backpropagate it here. Now this node is the one that actually produced this y hat. So this will multiply this by the derivative of y hat. So that's the internal function here. So then it will send it back there. This node will look at, okay, what was my contribution? I multiplied by the derivative of that, and I send it further. And at some point, let's say this connection here will intercept whatever was sent from this node. It will multiply it by the weight that it has, and that will be actually equal to the partial derivative of the entire network with respect to that node, with respect to that weight. And this is happening in every of each of these many connections. And so you get a partial derivative of this function with respect to each one of those weights at that weight. And it's quite incredible because in my previous picture, I had function with 2 variables. Now, in this day and age, people are able to train networks with more than 1 trillion variables. So you have 1 trillion variables function. Okay. So, and this W is a vector of length trillion. And you're able to compute the partial derivative of this function with respect to each one of those variables using backpropagation. And then you update. So you move all these weights in that direction that their own partial derivative tells them. So if that's exactly what was happening here. I move this one a little bit up, I move this a little bit left, and then we're closer to the local minimum, okay? Obviously, in actual applications, for example, it's not like we can put in the entire data here at once. So we put, it's called mini batching. You put small batches of the data in, you compute these partial derivatives, you update, and then you put another batch in. So technically, this gradient could change every time, and it does. And that actually slows down the process, but they say that it actually makes it also better because it, when it's more noisy, then it's less likely that you end up in some local minimum, because this landscape, now if I draw it from the side, this one, that looks like this. Now this is a very hopeful situation. In reality, the landscape is something like that. So you have a lot of these local minima, you get stuck in them. But when you have more noise and you have mini batching and dropout and shit, then it's avoiding those learning rate. There's many ways to avoid this local minimum. So you can actually end up in a better place, but you might still end up in a local minimum because maybe here is a better one. So that's an eternal problem. You cannot really solve this problem. This always have a local minima problem. If you solve it, you get famous, but I don't think you can solve it. One reason I think so is because I think it's an NP complete problem. But you can get close. You can get close. Okay. So I think that was it. Question 3. Question 4, ICA. Okay, what is the meaning of whitening? I kind of skimmed through it. I didn't really show you what it is for a reason, because it's kind of complicated. Requires more lectures, but we can go through it fast. Let's now have a vote. Somebody is asking me, is something the same as third question? That was about the Hopfield network. What?
I was referring to the first question, actually.
Oh, the very first one. Okay.
Yeah.
I didn't realize there was an exercise like that. Let's see. How do I find the exercise? Go to Moodle. Exercise 4.
Yes.
Third question. Construct a Hopfield network of 3 units. Yes! I didn't know we had this exercise actually, so. So yeah, okay, so we solved it. Nicoletta was doing this part, so I didn't follow this closely. So if you go to the model solutions, I suppose you will see the answer. Now I'm curious what is the answer. So I was about to ask, by the way, if people want to have a break. Can you like raise your hand if you want to have a break? You know, there's a raise hand option in Zoom. Nobody wants to have a break. Is that correct? Okay. Okay. Okay, so we'll keep going. Um, okay. So this is, let's see what's the answer. Oh, clan. Oh, that's a different thing. Because here, or at least in this solution, I don't know if this was this one is easier. Um, it doesn't say here in the exercise, but in the solution, it says, I don't know if Nicoletta spoke about it during the lectures then, but in the solution, they are designing a network where these input nodes are clamped, meaning you never change them. So if I force these to be always equal to my input, then obviously I can never change them. So I can only change the other one. So then I just use the same logic as with the standard perceptron. So I just make these weights. I don't see where the weights are defined here, but let's just have this equal to 1 and then the threshold equal to 2. So if these are both 1, then this will activate. If not, then it will not activate. And so then it will work just like a normal perceptron. But in my solution, which I presented half an hour ago, you don't require them to be clamped. So we just set an initial state, and then we wait the network to stabilize, and we saw that it will always stabilize to all zeros if we did not start with this equal to 1, and it will stabilize to all ones if these were set both to 1. But we have to also make sure that we set in this third one to 0. Otherwise, it might not work. In fact, based on my argument of the flipping states, I believe that it's impossible. If you're not allowed to set any other node, some particular initial state, I think you cannot really do it. But since we can set all the nodes to 0 except this 2, then we can do it. So this means that this plus the fact that you can actually do negation with Hopfield networks by putting a lot of negative weights, it seems that you can then always construct a Hopfield network producing any logical function, because negation and conjunction together are sufficient to make any logical function. The question is, can we do the compositionality as well? I think yes. Should think about it a little bit, but it looks like then Hopfield networks can implement any propositional function, which means that they're in particular Turing complete. So you can implement a computer with Hopfield networks. Okay, good to know. Should check the details. Okay, back to whitening. Okay, so when you have a random variable, you might want to normalize it. So, oh, it's not working. No, my drawing pad stopped working. Okay, so if you have a random variable x, it might be mathematically easier to work with it if it has zero mean and unit variance. So then you do normalization. Like this. Um, so after you do this, then suddenly it has zero mean and unit variance. But if this variable is multi-dimensional, then this is not so straightforward. Okay, it will have unit variance, but maybe you want the covariance matrix to be also identity. Remember the covariance matrix? Maybe you don't remember because we didn't actually work with it a lot. So if you have any a random variable which is multidimensional, so you have essentially several random variables which are not independent, let's say two in this case. So then the covariance matrix will compute the covariances. So how much do they covary? What is covariance? Covariance is, well, if it's the same variable with itself, it's just the same as variance. It's the expected value of the square. Assuming let's assume that they have been normalized, at least that the mean is always zero. So then if the mean is zero, then the variable x itself is this also measuring its own distance from the mean, and variance is the square distance from the mean square distance from the mean. So this is the variance, is the mean of the square of the second power. So on the diagonal, you have these variances. Here, you will have covariance between the first and the second, which is the expected value of this dot product. And here you will have the same thing. It's a symmetric matrix because covariance of x0, x1 is the same as x1, x0. So that's the covariance matrix. Now, you might want to normalize your variable so that this is identity matrix, meaning you rotate your data in a way, you rotate and linearly transform your data in a way that the covariances become just very simple. So covariance is essentially like correlation. So correlation is not independence. And I'll give you an example. I'll give you an example. So I'll give you an example. I don't know why this is not working the way I want, but okay. Again, I'm drawing a coordinate system with my mouse pad. Um, so imagine we have a data like this. I'm going to put some data like that. And like this. Okay. Now the covariance here is not identity, because because if you look at the first variable, then the second one will have much more weight when this one is positive, and when this is negative, then this will have much more weight over here. So then the covariance is not identity. When you make the whitening transformation, what will happen? It will transform the data in any possible way, in some of the ways which make the covariance matrix identity. There can be a lot of different ways that make it happen. And one way in this picture is to squash the diagonally. So we get a cross which looks like this. Okay. So this is whitening. And now what happened is now the correlations are all zero between the different components. And you also kind of squash it vertically and horizontally in such a way that those variances become identity. So then you have the covariance matrix will be just identity matrix. So intuitively, like if you look at the definition of covariance, let's say X and Y, right? So we have the dot product like this, and you take the expected value. Now you can see that because these both are symmetric around the zero, in the horizontally symmetric and vertically symmetric. So this average, the mean of this dot product is always going to be zero for these two different coordinates. So indeed, the covariance matrix is identity, but these are not independent. So this is an example where correlation or anti-correlation, so zero correlation, does not imply independence. Independence is a much stronger property. We can see it because at this point, the distribution of the other variable is like this. So if I plot it in a separate place, and this is the distribution of the other variable at this point. But if I move to the 0 point, then suddenly the distribution is like this. And when I move further here, then the distribution is again like this. So it's not independent, but the covariance matrix is 1, 0, 1, 0. However, it's much easier to perform ICA on this data than on this data. Plus, it's easier to prove mathematical theorems about ICA when we have done the widening than in this case. And the most important part is that after we've done the widening, it's enough to rotate the data to get the independent components, while here, well, actually here is also enough to rotate, but it's just because my example is so simple. But even then, this one is better, because if you think about it, here we have like this very long component, which has very large variance, it will dominate the algorithm. When you compute the kurtosis and stuff, these points on this line will overwhelmingly have like larger effect on all stuff that you compute, and the other one will have a much smaller effect. So there's a lot of noise, and so the convergence is slower, and that kind of stuff. But when you normalize it like this, then it's all equal. You are in the same range. Your variables are not like exploding, and so this will give you actually the independent components, which in this case, well, they're not actually fully independent anyway, but at least I would expect the ICA to give me something like this. It was actually quite difficult to come up with a really good example where you have which one you can draw, in a two-dimensional blackboard setting, which would be both independent, but when you do the whitening, then it's well, actually, I think if you have this data, then the square. I take my words back. You can actually. So if you suppose we have this data where we have this square like that, so the points are organized in a square like this. So whitening will rotate and squash the square a little bit in such a way that the correlations become zero. So basically the mass here will be equal to the mass here, and other way around. So you will have like this is white probably if you transform it sufficiently well. But then ICA will actually rotate it so that it's like this. And maybe the original one was like something like this. Okay, so whitening ICA. Like, let me make a new picture. Okay, so just quickly, let's have data like this. Whitening. Correlation zero, but not independent. Then ICA rotation. If we look at the book, there's one thing I missed somehow, and it is that I'm not sure if I missed it. At least I didn't remember whether I said it or not. But they assume, and I don't understand. By the way, I'm meeting Aapo Hyvarinen next Thursday, so I can ask him, one of the authors of this book. Anyway, they assume that the variances of the signal is 1, which puzzles me because how can you know that? Maybe they explain it somewhere else in this book. Maybe this assumption doesn't really hurt, but they do assume it. And once you assume that, and you whiten the data, then you have an interesting property, which is that you take A times S. So this is your data. And we assume that this data has been whitened. So basically this has been multiplied by a whitening matrix. So instead of multiplying it, I just put a hat and I say this is now whitened. then the covariance of this will be also identity. The covariance of this will be identity. But that means, sorry, what did I want to say? What do I want to say? So the covariance of this is identity. This is just by definition of whitening. So I transformed it so that it is identity. And what I want to say is that from this, it follows something interesting. The covariance behaves in a way that if I take a covariance of some matrix times some vector, it's the same thing as this covariance, this matrix times covariance of S, and then times the same matrix transpose. This is just a general property of covariance, always works. But because we assume that the variance, or like in this case actually, because S is just a vector, it's not covariance, it's just variance. Variance. Now we assume that it is 1, or they assume that it is 1. And because it's 1, now this is the same as this matrix times its own transpose. And that is identity by the assumption here. When we have a matrix which multiplied by its own transpose is identity, that is an orthogonal matrix. So it follows after whitening that this unknown matrix is actually a rotation. It doesn't have any other properties. It's not bending the space in any other way. It's just a orthogonal matrix. Much easier to deal with than any matrix. And so when it's an orthogonal matrix, we know that the inverse is also orthogonal because, rotation, inverse of rotation is also rotation. Now, orthogonal is not exactly rotation, but it's almost like rotation. And that means that when we're looking for so remember the ICA equation, now we're looking for some matrix V such that when I multiply X, I would get S back. So I'm looking for the inverse of A. Now I have whitened this. So now I know that it's orthogonal. And that's why I know that the matrix that I'm searching for is also orthogonal. And that is very useful because now the space of matrices you're looking for is much smaller than before. Like if before you were looking for any matrix, now you're looking for orthogonal matrix. But that's the real benefit of whitening for ICA. Again, you can do ICA without it, but it's going to be slower. It's going to be not always correct, noisy, etc. If you do whitening, faster, more precise, and you can prove this thing, which means that your algorithm can be made more efficient. Okay. Move on. Another question about ICA. Okay, so a very quick answer. So the question is, ICA is a statistical method for extracting original signals from the mixture. I was wondering if you could share some insights into how it can be incorporated into machine learning. So what I know is that, well, first of all, it is machine learning already. But for all I know, ICA is often a very good pre-processing step for deep learning. Why wouldn't you extract the independent components before you start training your incredibly complex network? So it's definitely in some cases useful to do. Let me think of an example. I mean, take music. Suppose you want to make a neural network. You have recordings of bands playing, and you have a neural network, and you want to be able to detect the melody or the piece, or you want to detect some other properties of the music. Is it jazz, or is it classical music or something? I would expect that if you perform ICA first, so you extract the different musical instruments as separate data streams, you will significantly simplify the job for the deep learning network. Instead of just feeding in the mixed sound, make ICA, extract the different components, the cello and the piano and the saxophone and the voice or whatever, and then feed that into the neural network. It's going to be much easier for it to classify your music. It's just an example. I don't know if they make even like ICA layers in the deep neural networks. Because ICA is unsupervised. It's a different, it's like in a different spirit. So it's not clear how would you even use it within a deep neural network, because you don't apply gradients or anything. I'm curious. No, no, that is different. They just propose an algorithm to do ICA. By the way, I know that Aapo Hyvärinen did nonlinear ICA, which is kind of interesting. Here we go. That's very interesting. So this is a proposal for like unsupervised deep learning. They stack those ICAs. I'm very surprised that this date here is 23. I thought this was made earlier, but maybe this is a new paper. So check this out. What can I say? They do nonlinear ICA. It's very cool. That means that your mixing is not a matrix, but it's some more complex nonlinear function, and you can still get out the independent components. The trick, actually, I can imagine that the trick is that independence is preserved when you apply, at least on the individual coordinates, any function. So if x and y are independent and f and g are any functions, then f of x will be also independent from g of y. That's a very strong property of independence. So maybe they're using something like that, using that as a part of the the application of the central limit theorem. Now you have to kind of have a nonlinear function. That's pretty awesome. Check this out. That's all I can say about this question. Okay, good. Let's move on. Then we have reinforcement learning question. Now, as far as I understand this question, I don't think we need to read this all. I can explain what I think it is, and if I explain it wrongly, then maybe the person who asked it can correct me. So we have a world with three states, and transitioning from this state out of that state has value 4, and every other transition has value -1. I don't remember exactly all the details. We can check it up, but it doesn't really matter. The point is that it is symmetric. We can check what was the actual exercise. Wait, that's not it. Wait, that is it. No, it's the last one. Right, okay. Okay, reward 0, or if you bump into the wall, then it's -1. Okay. Okay, so if I'm trying to bump to the wall, I have left and right actions. If I bump into the wall, it's -1. If I transition anywhere, it's 0, except if I go out from the middle state, it's going to be 4. Okay, very good. Now, it's symmetric. So when I solve the maximality equation, the Bellman maximality equation, I get a value function which tells me the value of different transitions. That's the exercise, but you get some value here. So it's not going to be 4 because the value function incorporates the discounted expected rewards from the future. So it will be something like, I don't know, 6, I don't know, something like that. 6 when you transition here, because you have 4 plus, and then discounted rewards, and when you come back and go do it again, and etc. And you have the exact same thing here for the value function, the optimal value function. Now, the optimal value function, you can think of it as a gradient. And then when you follow this gradient, that's how you get the optimal policy. That's about it. So, for example, when you're here, your immediate reward is 0 if you go right, and it's -1 if you bump the wall. But actually, if you go right, your value, so remember the value will be like the gamma to power n times RT, and t goes from 0 to infinity. So you look into the future, and you see what kind of rewards you're going to get when you follow your policy. But in the maximality equation, you don't have the policy, you just have an equation for the value function. And then you can solve it, and you get a maximal value. But the thing is that because this world is symmetric, then the value of going left and going right is exactly the same. So a policy which would go left, right, left, right, left, right forever is as good as the policy which goes left, right, right, left, left, right, right, left, etc. Of course, this one is more complicated because you have to store more memory and everything. So you would probably go for the first one. But both of them are optimal, and both of them are following the gradient. And now I think that the question is boiling down to the question, what do you do if you have two different actions that have the exact same maximal expected value? And I think the answer is that you just randomly select one, or you take the one that is smallest in order, like you order all your actions. And in this case, you only have two actions. So you could say, if the values of taking these actions is the same, I always pick left. So then you will be stuck in this part of the world, going back and forth. If you say, oh no, if the value is the same, I pick always right, then you will be stuck here. And if you say I pick it randomly, well, then you are going to be going, you always go bounce from the limit, so from these corner edge states, boundary states, you'll always bounce to the middle, and then you will randomly go to one of the other ones, and then you bounce back to the middle again. So that's what I understand from this question. By the way, here is the maximality. No, where is the maximality equation? I put it out here. Here is the maximality equation. So the best possible, so the maximal value at each state can be obtained like this. And this is kind of a circular equation because you have V star here and you have V star there. But of course you can solve it. And when you solve it, you just get this gradient. Like you get like how valuable each state is, and then you go from every state, you always go to the one that is, the most valuable one. And sometimes you have many different options. Does that answer the question? Or okay, let's move on.
I have a question from that
Please.
question itself. So in this Bellman's equation, we have a probability of if we are in state S0 with the action A, there's a probability which includes that in the equation. Going to state S dash with reward. So in this question, how can we get those probabilities? That was my question.
Can you say it again, please?
So in this Bellman's equation, there's a probability of being from state A and taking the state S and taking the action A and moving
Yeah.
to state S dash with the reward of R.
Yeah.
So in that question, I was confused on how to calculate these probabilities.
These ones?
Uh, yes.
Okay, let's look. Let's look at that. So, okay, I get it. Okay, so let's calculate this probability. So let's I give you an example because I shouldn't be solving the entire exercise for you, but let's put it here. So, for example, okay, let's see what does it say. Let's put it like this. Just bigger. No. Okay, so because in this exercise, it says that the actions left and right move deterministically left and right, and the rewards are also being deterministic. Okay, I guess it doesn't say it directly, but it doesn't speak about probabilities here. So that means that the probabilities are always just 1 or 0. So if we're asking about what's the probability of getting into state S0 and getting reward 5, just an example, given state S1 and action left, that probability is 0 because there is no reward 5. Going to S0 with and getting reward 0, no, sorry, 4. Yeah, 4 is the correct one. Given S1 and left. That's probability 1, because if you are in this middle state and you go left, then we know from the description that then you go to the S0 and you get reward 4. So that's exactly what will happen. So with probability 1. If I say, what is the probability that I go to state S2 and I get reward 4 given the same conditions, S1 and left? That's 0 because I don't move to S2 from S1 if I go left. But if I look what's the probability of going to S2 and getting reward 4 from S1 applying the action right, then these probabilities are going to equal to 1. So this makes this equation here much more simple. It means that this whole part will just reduce to several options. Everything else will be just 0, except for the selected ones where you do the correct thing, right? So that's why you can write this out very easily. Otherwise, it would be super complicated.
Yeah.
Is that what you
Yes.
Okay, good.
Yes.
Okay, so we're basically out of time, but there's one more question, but the last question is not actually really related to the course. Put it last because of that. But I also don't know if I can answer it. So here's the question. I'm currently reading oh, by the way, does someone else have now a question about the course? Something about the course. Last chance. No? Okay, well, so the last question, I can, of course, show it, but I'm afraid I don't know if I can even answer. I'm currently reading a book on statistical learning methods, and the initial focus is on linear regression, okay? The book suggests that after performing a linear regression, one should investigate potential terms and their corresponding p-values to assess the validity of the identified hypothesis. Right. And manually exploring all these combinations is very inefficient. So, right. So I would have to see that book, and I would have to see more about what it's saying, because I'm not sure why I even understand what are the logarithmic or nonlinear terms. But essentially, maybe the quick answer is that, well, no, in our course, we didn't really do things like this. But I understand, like the question is, if you have data which is not linear, and but you apply linear regression, now you can ask, what if that was a, you know, bad idea? So you check if adding two values from the data, if it behaves linearly. Linearly means that a linear function will satisfy x plus y equals L of x plus y equals L of x plus L of y. And if the function is not linear, it will not satisfy this. So you can check, you can test that. And yeah, but this is not really part of this course. So yeah, I don't really know. I also don't really know the answer. So um, I suppose there are a lot of automatic methods to do that with algorithms, but I don't know what they are. Right. So I guess we're done. Somebody says something in the chat. Okay. Nice. Okay. Thank you all for your questions. Everyone who sent me a question will get a point. And see you on Monday, except I'm not going to be there, but on Monday is the exam. And then good luck with everything, and I hope you get good points and get a 5 and move on with your lives in a successful way. Thank you. Thank you. And have a good weekend. Bye bye.